So we are given a root of a binary tree, and we need to return the leftmost value of the last row in the tree. So our inputs is a root, which is a tree node type. Some immediate standout points is that this could be null, could be none, but we'll handle that later. The output is just integer. It is the value of the bottom leftmost bottom leftmost, so, or leftmost value in last row. Okay. So in this example, the leftmost will be this one here, since the last row is this one right here, and left foot of that is 1. In this, I immediately thought it was just 4, but that would be the case if the 7 wasn't here. Because the 7 is here, this is the last row, and you want to take the leftmost value. Since there's only one value here, it's just 7 as itself. The constraints number of nodes can be just very large, and value can be any value, so there's not much, nothing new there. So instinctively, the most brute force way I can think about it, or the way I would solve this, is go through every, you could do like a BFS way of doing it. So go through every row and save and save. So BFS, let's see. Save the leftmost value in that row itself. Buffer search is good because it goes row by row. So you do 1, you say 1, you go 2, save 2, you do 4, 5, 6, you'd say 4, and then 7, you say 7. I was thinking some optimization we could do is just every row we save the left value in that, but that wouldn't be the case because if you have 1, if you have 2 here, 2 and 3, if you only say this 2, you'd only end up going 4, but you actually need to take the right of this and then go down. Another way is just DFS itself, and you just do go as far left as possible, and save the depth and value. But I don't think this would be good because the logic behind that would be you go 1, and then you take the leftmost value at 1, so that's 4. But then you need to take the leftmost at every node itself. So if this 6 had another value here, let's say like this had 8 here, what would be the logical difference between 7 and 8? But BFS does that row hierarchical for us. So I think I'll do this BFS for now. So the logic behind that, and I can't think of any optimizations from there because your enemies need to go to the last depth. So, and there's no repeated work in the sense, so there's something that's being lost. And it's not clear, at least from right now, if like where the deepest point is, right? So like we can't say choose specifically this right side because we know it goes left, because this 4 can go a lot farther down. So that, let's write out the pseudocode. So you would have a queue. You just search that up. Search this up. And you initialize this with the root. And then in the leftmost value, it's going on. I guess if there is, we need to check what happens if it's, so if there's none. If it's none, I guess we just return this value. So while q, we save the first, for each element in the queue, save the first element, and then and then we have a new queue here. new q is this. For every child in element to new q, you need to add left and then right. And then from here, you just return leftmost value. I think that pretty much makes sense to me. So let me double check how to check. Okay, collections.dq. Okay, sweet. So q is this collection.dq. Base auto. Okay. And then we have output is equal to none. Right, this is our leftmost value. And while we have still have a valid q, your new q is collections.dq. I guess it's not to be like this. It can just be an array, right? And we treat it as like a q, but you don't have to like pop from there. So for I in range length of q, if I is equal to 0, output is equal to for, okay, wait, so sorry. I's index element is equal to, or node is equal to q at I. So if I is equal to 0, then node dot value is, you said output, you know, else new q dot append node dot left q dot append node dot right. And from there you just return output, I believe. So let's go through this. So you have, and then we also need to initialize with the root. Okay, so we initialize q with root, and the output is none. And then while this is a valid q, the new q is empty. Oh, and then we just set q is equal to new q. Okay, so q is empty. For every index in the queue, we get the node at that element, at that index. And if our index is 0, that means you have the leftmost value of the queue, right? Or leftmost value of the row. So you set that output to that value. If not, and we see that, but aside from that, we need to add all the children. So we'd have the children, so it had 2 and 3, and then go to the next index, but there's no other index. And then we add the new queue, and we have set the q to new q. So now our q is 2 and 3. 2 and 3 goes. The first index is 0, so that's, it'll save 2. But then it'll set the value 4, 5, 4. Oh, I need to check if node is none. Okay. If node is none, continue. Okay. So we append left. If notice, you go right. But this is none, so we just skip this. We save this left. And we do 5, 6. We had 5, but 4. We had 4, 5, 6. Okay. And from here 4, we add its none children. 5 adds. This has none, so we skip that. We have 5, it adds 7, and then none, and 6 adds none. And state 4, and then yeah, okay. I think it should figure on this. This is wrong. It return. Oh. Okay, I see. So if index, so let's not do this. We only add let's do this instead. If node dot left, if node dot right. Okay. Awesome. Sounds good. Thank you.